energy of a charge distribution, and what we have seen in the previous two lectures is that this is given as 1/2 integration Vr rho r dV, or 1/2 1/4 pi epsilon 0 integration double integration rho r prime over r minus r prime dV prime. As we learned earlier, we also like to think in electrostatics, and this becomes very important later, in terms of electric field. So think in terms of electric field. Conceptually, I'll just recall what we had said earlier. What we had said is, given a charge distribution, I can think of this creating a field around. And a charge distribution and field are uniquely related given boundary condition. So if I know the charge distribution and the boundary condition, I know what the electric field is. And vice versa. If I know the electric field, then divergence of electric field gives me the charge distribution. So can I think, if I'm thinking of this charge distribution giving rise to this field all around it, can I think of this energy as if it has been stored in this electric field? That will be a conceptually different way of thinking about it. And let us work on that. And in fact, what we will see is, I can actually describe this energy as if it's stored in this electric field, right? And they'll give me charge energy density per unit volume. This becomes conceptually very important later when we talk about electromagnetic waves or fields propagating. Then we'll see that these fields, as they propagate and new fields are created, energy also gets transported by it. So it's important to think in terms of this energy being carried by the fields. So that is what we are going to establish in this lecture. So let us see what we had worked on. We said that energy, and I'm using this E, do not confuse this with the electric field, and to remove that confusion, let us write this as W, the work, is given as 1/2 integration Vr rho r integrated over the volume. Now I'm going to do some mathematical trick. I'm going to write rho r as minus del square Vr times epsilon 0. This is the Poisson's equation. If we do that, then I'm going to write W as 1/2 integration Vr times del square Vr, this is vector, dV, and there's a minus epsilon 0 outside. All right? Vr, del square Vr, since del is a differential operator, I can write this as divergence of V, gradient of V, and this will give me gradient V dot gradient V plus V del square V. So I have to subtract that grad of V square from this. And this I'll leave for you. Should check this. All right. Remember, this del operator is actually a differential operator. So I can write this, and you please check this, because now I'll be doing it in all three components. And therefore, using this, I can write the work as minus epsilon 0 over 2 integration of divergence of V del V minus grad of V square integrated over the volume. For the first term, I can now use divergence theorem. What does the divergence theorem tell me? it tells me the divergence of a vector field integrated over the volume is nothing but A dot ds over the surface enclosing that volume. And therefore, I can write this work as minus epsilon 0 over 2 integration over the surface of the vector field which is inside V gradient of V dotted with ds, minus minus will give me plus, plus epsilon 0 over 2. And what is grad of V? Let me show this here in the red, is nothing but the electric field. So this is electric field square dV. If I am talking about a large space, then far away, the surface is going to be at infinity. This V goes as 1 over r. Grad of V is the electric field which goes as 1 over r square. So this term will be going as 1 over r cubed. ds goes as r square. So in the limit of r going to infinity, this vanishes as 1 over r. So this goes to 0. And therefore, I get the energy or the work done as epsilon 0 over 2 integration E square dV, which I can write as integration of 1/2 epsilon 0 E square dV. This is a quantity when integrated over the volume gives me the total energy, and therefore this quantity must be energy density. So now I can think if there is a charge distribution, all right, then the energy density that it gives rise to all around, including the space in which this charge distribution itself sits, is equal to 1/2 epsilon 0 E square. If that is the energy density, the total energy comes out to be this energy density integrated over the entire volume. So now I am thinking of this energy being sitting in this electric field, or this electric field carrying this energy. Let us solve one example of this. You have learned in your 12th grade, if I have a capacitor of capacitance C, and if I give voltage V to this, what is the total energy required to do so? It is V is the potential somewhere, let's say the potential given is up to V0. So V, charge brought in is C dV 0 to V0, which becomes 1/2 C V0 square. That is the total energy in this. Now, according to what we just now said, the energy density is 1/2 epsilon 0 E square. Now, in a parallel plate capacitor, the only place where the electric field is between the plates. Everywhere else is 0. And this electric field magnitude is nothing but V0 over D, where D is the distance between the plates. And therefore, the energy density in this case is going to be 1/2 epsilon 0 V0 square over D square. The total energy is going to be the volume, which is the area of the plates, times D times the energy density. And this you can see immediately is same as this, with C being equal to A epsilon 0 over D. The next example I take is that of a charge shell. On which there is a charge Q. Now, if you calculate the energy with using the formula 1/2 VR rho r dV. In this case, rho r happens to be the surface charge, which I can write as sigma times delta r, only r, not vector r, minus r. This has dimensions of 1 over r, therefore this has dimensions of sigma times delta r minus r has dimensions of 1 over the volume. So work is going to be therefore 1/2. If I put the integration v r sigma delta r minus r times 4 pi r square dr integration, which is 1/2 v at r times sigma times 4 pi r square. 4 pi r square is nothing but q. So this is 1/2. V due to this q is nothing but q over 4 pi epsilon 0 r times q. So total energy is going to be q square over 8 pi epsilon 0 r. A known result from your 12th grade, right? So this is the energy of the system. Let us now calculate this using the electric field and the concept of energy density. So for the shell, the electric field magnitude outside is q over 4 pi epsilon 0 r square. E inside is 0. And therefore, I get W equals integration epsilon 0 over 2. E square will give me q square over 16 pi square epsilon 0 square r raised to 4 times 4 pi r square dr, and this integration is going to be from r to infinity because inside the field is 0. Let's cancel a few terms. This 4 pi cancelling with this, 16 pi square gives me 4 pi. Epsilon 0 cancels with this, gives me epsilon 0. So I end up getting 1 over 8 pi epsilon 0, that is this half, this and this, q square integration this r square with this gives me 1 over r square dr over r square r to infinity, which is same as q square over 8 pi epsilon 0 r. Same answer as earlier. As the final example, I take a problem of uniformly charged sphere. Where the density rho is uniform over a sphere of radius r. This is the problem we solved earlier by calculating 1/2 VR rho r. In this case, the magnitude of electric field is rho r over 3 epsilon 0 for r less than r, and it is equal to total charge q over 4 pi epsilon 0 square for r greater than r. Now when I do the integration epsilon 0 over 2 mod e square dv, now it will be from 0 to infinity. Remember this part I have just done in the previous problem, this integration. So I can write this as 0 to r epsilon 0 over 2 rho square r square over 9 epsilon 0 square times 4 pi r square dr plus integration 1/2 epsilon 0 q square over 4 pi epsilon 0 r raised to 4, this is 4 pi epsilon 0 square times 4 pi r square dr. The second integral I just now did in the previous problem. So this is nothing but q square over 8 pi epsilon 0 r, because this limit is from r to infinity. So it's only the first integral that I'm going to calculate now, which is epsilon 0 over 2 integration rho square over 9 epsilon 0 square r square times 4 pi r square dr 0 to r. Let's again cancel a few terms. This becomes epsilon 0. So I get 1 over 18 rho square, which is nothing but q square over 16 pi square r raised to 6 times 9 times 4 pi over epsilon 0 r raised to 5 over 5. Let's cancel a few terms here. This 9 gives me 2. This 4 pi gives me 4 pi. R raised to 5 with this gives me r, and therefore I am left with 1 over 2 q square over 4 pi epsilon 0 1/5 r. This added to the previous expression will give me the total energy, and let us do that. So total energy W is going to be q square over 8 pi epsilon 0 r plus q square over 8 pi epsilon 0 1/5, which is nothing but, or there is an r also, q square over 8 pi epsilon 0 6 over 5, which is 3/5 q square over 4 pi epsilon 0 r, which is the same answer as we had obtained earlier. So what I have tried to show you in this lecture is that you can think of the energy of a charge distribution as if it is stored in the electric field produced by this with the energy density 1/2 epsilon 0 E square, and we have seen through 3 examples that this gives you the same answer as we obtained earlier with the direct formula. I end this lecture by discussing something which may have bothered you throughout this lecture, and that is, when I was calculating the energy due to charge on a shell, remember I wrote the energy to be minus 1/2 integration grad of divergence of grad V plus 1/2 epsilon 0 E square. This term gave me q square over 8 pi epsilon 0 r, and I said conveniently this term is 0. But some of you may have noticed that I am doing an integration from r equal to the radius up to infinity. So you may be wondering what happened to this surface term, because this divergence is supposed to give me a surface term. This is a slight subtle point, because this divergence will give me V grad V dot ds over surface of shell plus surface at infinity, and that gives me 0. I'll show you now that this also gives you 0. You see, the surface of the shell is slightly inside, because when I'm doing this integration it includes all the charge distribution. So I'm actually doing this integration from this blue surface which to infinity, and this blue surface and infinity region in between includes all the charge distribution. Now on a shell the potential is a constant, and therefore this integration becomes V outside grad V dot ds, which is nothing but V integration E dot ds, but then this blue shell does not include any charge, and therefore E dot ds is 0 by Gauss's law, and therefore this term also vanishes. Think about it. It may have bothered you throughout the lecture, but now I've given you the answer.